All right, class. Module 4 is the next section of the class that we're going to look at. Module 4 is multiview drawing or orthographic projection. This is going to cover chapter 6 in your textbook. And what I'd like to do is just go through some slides here that will help you to understand some of the details and some of the standards that we're going to be looking for in the orthographic drawings in this section, and actually in the sections after this, which is where we're really turning the corner in the modules 4 and 5, 6, 7, 8, all the way through 9 and 10. Where we're starting to establish kind of the ground rules for how a drawing, an engineering drawing, is supposed to look. The standards, the guidelines, the best practices, so on and so forth. So let's get started with this. Some of this is going to be familiar to you because we've already been sketching with this kind of concept, the concept of orthographic projection. Some of you have already been exposed to this in high school or in other classes, but we'll go through it nonetheless. Hopefully, I can fill in any details that you may be a little bit hazy about. So the whole idea with orthographic projection is we have a problem when we're trying to describe real life things that we want to build or things that have already been built and we need to represent them accurately. And that is to say, objects in the real world are three-dimensional, but when we have to represent them on paper or even to some extent on a computer screen, we're limited to two dimensions, right? Height and length, or length and width, or any of those combinations. So the challenge is, how do we represent a three-dimensional object on a two-dimensional surface? And the way that we do that is we use orthographic projection. And orthographic projection is basically a way to look at a three-dimensional object and to represent or draw two-dimensional views of that object. All right. And by accumulating these two-dimensional views, we can paint a completely accurate picture of the object. So we can represent a three-dimensional object with a group of two-dimensional views. Okay. One of the things that you're going to have to understand is how you can view the object while you're trying to imagine it, right? If you can imagine that you have a three-dimensional object in your hand, how do you view it to create the front view? Okay. So you basically are going to hold the object in front of your eyes. And you want to make the object, the face of the object, the front surface of the object appear flat to your eyes, right? So it's going to be parallel to your face, perpendicular to the light beams coming out of your eye. All right. So that creates the front view. The top view is going to be a rotation. So imagine that we still have the object in our fingers like this, and we're going to rotate it slowly until we're looking at the top of the object. And there we have the top view. All right. Moving on to one of the side views, in this case, the right side view. Again, we're going to start with the object in this orientation, and then we're going to rotate the object until we look at the right side. And so that's all it is, really. We're going to be viewing the object, the three-dimensional object, by making these rotations. Now, the challenge here is a lot of times these rotations, these manipulations of the view have to happen in your mind, right? We don't have the objects to hold, okay? Sometimes we're designing them, sometimes we're just imagining them. So there is the challenge and where you really need to practice, and that is to get a good mind's eye view of the object, the three-dimensional object, okay? You often hear talk about a glass box. One way to help visualize how the views are arranged on an engineering drawing is to imagine that the object is surrounded by a glass box, right? The glass box is going to have 6 panes of glass. a top pane, a front pane, a right side and a left side pane, a bottom pane, and a back pane. All right. Now, as we do that same rotation with the object, right, we're rotating the glass box too, along with the object now. Okay. And we're going to trace out on each glass surface the view that we see as we rotate the object. So the front view would look like this. The top view would look like this. These are all two-dimensional views. All right. And so this shows us that we're going to have what are called 6 principal views: top, front, right, left side, bottom view, and back view. That's 6 principal views for our object. Typically, we deal with 3 regular views, right? And those, again, typically, not all the time, but typically those are the top, front, and the right side view. All right. We use, this is kind of an aside, but you might run across this term in your reading, third angle projection. This is third angle projection being shown right here. That's the standard in the United States. In Europe, they use first angle projection. We are not going to do any drawings in first angle projection, nor am I really going to talk about it, okay? So we're going to stick with third angle projection here. So then the challenge then is to unfold that glass box, and that's going to help us visualize not only the object, but how the views are arranged. So here we have the glass box. Now we're going to start to unfold the panes, right, or unfold the glass box. And we end up with views arranged like this. Now the critical thing here is that by using this method, the views are aligned, right? Notice that the bottom of the view, we can see the bottom surface in the front view is right there where my mouse is, okay? That bottom is aligned perfectly right there all the way across these views. In fact, the right surface right there is also in the top view and in the bottom view and the left side. Basically, every surface must align. Now, this is a rule in orthographic projection and definitely something I'm going to be looking for in your drawings. The views must align, okay? So the front view and the right side view and the left side view, those are all going to align, top and bottom. The top view and the front view and whatever views we have, they're all going to align as well. Okay, so that is a key feature. This is just a little slide explaining the projection of the object, what I talked about a couple slides ago with the glass box and how we trace out the view of the object. So here we have, this is called the plane of projection. And this is basically a glass pane from our glass box, a glass surface. And these lines show how the object is traced out, all right, to create this two-dimensional representation of it on this glass pane, I should say. Okay. So, some of the things to note when we create an orthographic projection. In our front view, the adjacent view is going to be the right side view and the top view. All right, these are called adjacent views. All right, these lines right here, these broken lines going up here, are what we would call our vertical projectors, right? They help us to project, in this case, this hidden, well, let's start at the top. The circle, the edge of the circle is projected down to the front view and represented with these hidden lines, okay? Now, in AutoCAD, when you're drawing, oftentimes we will draw these projectors down to help us visualize things and to help us to keep things aligned. But note that this hidden line right here, this broken line, I should say, the projector, they're not shown on the actual drawing when you're done, okay? Then we also have what are called common measurements, okay? So this depth right here in the top view, that is equal to this depth right there. And in fact, it's the same dimension, right? So that's important. That can help us to find some features or to draw things more accurately. All right. So oftentimes we're going to be having to figure out what are the necessary views to draw, right? In the assignments that we're going to be working on in class, I'm generally going to give you the views that are needed: top, front, right side view, left view, whatever. I'll specify that for you. But in the real world, when you're trying to design something, when you're trying to replicate something that's already been designed, to draw something orthographically that's already been designed, you don't have an answer key, or you don't have an instructor telling you, hey, I need these 3 or 4 views. So what are the guidelines for figuring out which views are necessary? Well, first of all, we want to show the shape most clearly in the views, right? We don't want to use any views that end up being confusing, all right? Oftentimes, that means that we want to choose views that have the fewest hidden lines, okay? So the top view would be better than the bottom view, because this surface in the bottom view would be hidden, and that's unnecessary because in this view, it's a visible line. Visible lines are generally better than hidden lines, okay? Sometimes it's unavoidable. In the right side view, we have this hidden line. There's no way that we can get around showing that hidden line. So we want to have the fewest number of hidden lines in our views without omitting any. We can't just, decide that we're not going to draw hidden lines. And then we also want to show the object in its normal, stable, or operating condition, okay? So those are just 3 guidelines to help you identify which views are necessary. When we're drawing the views, sometimes we do have some leeway in terms of view arrangement or view placement. It's not all the time that we have this, but sometimes we do. And when we do have that openness or freedom to choose the arrangement of views, we obviously want to pick the arrangement that's going to give us the most efficient utilization of the space. So you can see in this example over here on the left-hand side, we have our typical top, front, and right side view here. But notice the right side view is developed from or projected from the front view. And what happens here is 2 things. One, we end up having a view that's much too close to the title block over here. And we end up having a lot of open space here. Now, generally speaking, open space is not such a bad thing, but in this case, the view being so close to the title block is going to be very problematic. One thing that we have to consider, and we'll be actually doing this a few modules from now, is dimensioning of the object. And you can clearly see in this view, there is absolutely no room to dimension this object. So this is really not a good arrangement of views. So how can we change that? Well, instead of projecting from the front view, the right side view can be projected from the top view. Notice, compare this view in the left figure and this view in the right figure. The right side view is identical. It is absolutely unchanged. The only difference is the side view here in the blue figure is rotated. Why? Well, because it's projected from the top view. All right. So this is a much more efficient utilization of space. We clearly have enough room for dimensioning. We're not crowding the title block. Okay. So where you have the option, you should definitely choose your view arrangement wisely. Okay. To use space in a good manner. We don't always need 3 views. Okay. So in some cases, we have situations where in this upper left-hand figure, we have 2 views of an object, of this cylindrical object right here. You can see it in the front view here, but we have a choice between the right side view and the left side view. All right. Now, the left side view should be avoided. Why? Well, because we have too many hidden lines, right? So all the features that are going to be in here are going to be shown with hidden lines. That's not good. So we want to show the right side view. This is much better because we have no hidden lines in the right side view. Okay. Sometimes we don't need a third view. So in the figure on the right, up here on the top right, only 2 views are necessary. So we have a top view and we have a front view, right? The right side view of this part is not necessary. It's not going to show us anything that we don't already see in these other views. Same thing with the object on the far right-hand side. Only two views are required here. A top view is going to be identical to the right side view, right? No difference, right? So again, two views. In some cases, a single view is all that we need. So for parts that are thin and flat, such as this part on the bottom left, this is a perfect example of a single view part where the thickness of the part would be noted down in the drawing notes. Okay. For cylindrical parts like this, we don't need a second view or a third view because we understand that all of these are stacked cylinders. We have all the dimensions, so everything's good here. So sometimes we can get away with one view, sometimes two views, and that helps to ease up our drawing, make it a lot easier to understand and save time and space in our dimensioning. Okay, so partial views. Sometimes we can actually get away with omitting certain features in our drawing. So that includes cases where we have symmetrical objects, like here on the top left, we have a cylindrical feature, right? So we have in this case, a left side view. If we call this the front view, then this would be a left side view, right? And in the left side view, we're using a line of symmetry, right? This line, this center line with two horizontal lines on the bottom and two horizontal lines on the top. That's called a line of symmetry. And what we're doing is we're saving space by only showing the one side of the object, in this case, the right side of the object. Now, it is important to show the right side of the object here because we're showing the front view over here, okay? If we showed the left side of the object, then this view would not be correct, all right? In the example just to the right of that, we're using a partial view, and actually this is what's called a viewing plane. So these arrows and this line right here, this thick broken line with the AA on either side, this is called a viewing plane. And it basically says to the person reading the drawing, hey, I'm viewing this object right here from this direction. And then this is the view that I see. Now notice in this view, AA, first of all, it's labeled AA. It must be labeled AA. And secondly, we're allowed to omit all the features behind it because we're saying with the viewing plane that we're only showing what's important in this view. All right. And here's a couple more examples with partial side views. So in this case, we have kind of a U-shaped object with detail on the left and detail on the right. So we could call this our front view. And the left side view, if we showed all the features in here, that would be the hidden lines and everything, it would be a very confusing view. So what we're opting to show is a partial view with only the visible features of the left side and the hidden surface. So what are we omitting? We're omitting all the hidden features for this section of the object. And likewise, on the right side view over here, this is also a partial view, because clearly we're omitting all the features that we see on the left side of the object, right? So this is just a way to greatly simplify the object, to make the object much more understandable for somebody that's reading it. We're not leaving out any detail that is going to make the object confusing or misleading or anything like that. So this is perfectly acceptable. Another example of partial views, this is very similar to the last one, but you can see this, just another example of a partial left side view, a partial right view, and a full front view. Okay, this is a full front view. And another example of partial view, this shows some variation here. So here we have kind of this L-shaped object right here. And so we're using a partial left side view and a partial bottom view. And if you're wondering why would we show a partial left side and a partial bottom, well, the answer is if we were trying to draw the rest of this object, that is to say the full projection of this object on the left-hand side, this detail down here would get really messy real quick. There'd be a lot of hidden lines, a lot of curves, just a lot of messiness. Same thing with the bottom view. If we showed the full projection of the bottom view, it would be messy over here. And so to avoid the mess, we're allowed to use a break line. This is called a break line. It's drawn on the visible layer or the thick layer, and the break line is there. Here we have a cylindrical feature, right? It's a base with a cylinder rising out and then 4 ribs on either side. And we can show it 2 ways. We can either use a center line, like we did in this last object over here, where we use a line of symmetry. Basically, a line of symmetry and a center line are the same thing. But here we're using the center line to separate the left and right partial views. So we're only showing the left side of this view. Or in the case where we want to show, notice that we're showing here the full thickness of the rib, right? Here we're not showing the full thickness of the rib, right? So maybe that's important. Maybe these ribs have a different thickness than this rib over here. So we want to show them. So how do we get around that if the center line is right there? Well, we push this a little bit further and we use a break line to separate the object. Okay, so 2 more examples of a partial view. We can also, in cases where we need to show a larger detail, right, we can show an enlarged view. Okay, so an enlarged view is just an area of our drawing that we're able to focus on. We're basically able to pull it out. So in this, we have a regular view right here, and we want to show this, I guess you might call this a keyway or something like that. We want to show that so that we can dimension it so it's clear. So we're going to point to it with a leader. We're going to say see view A, and then we're going to call it out over here and enlarge it. Now, one of the rules when we're showing an enlarged view is you must include the scale. Okay, so here we have, and with an enlarged view, the scale is going to be larger, right? So here we're saying we're enlarging it by a factor of 3. So it's a 3-to-1 enlargement. It should be oriented in the same manner as the main view. We don't want to rotate it because that would just be confusing. So here we have view detail A. Now notice in this one, this is a very small view, and we're showing a much larger detail view. This is 5-to-1. And so you can see it much more clearly. Here we're kind of showing schematically the rivets. These are rivets over here. But here we can show clearly the detail on that, plus this L bracket, this angle bracket. And likewise over here, this is a section view, okay? But we're using a kind of the circular arrow feature. You'll see this a lot with enlarged views. And then there's a B there. So we're creating enlarged view B right there. And again, this is scaled 5-to-1. Okay. All right. So we don't often run across cases where we have intersecting cylinders, but where we do, we can simplify the requirements of our drafting by recognizing that we, again, don't have to make true projections. So if we look in the top view up here, we have a rectangular bar that's sitting on top of a cylinder. And if you look closely in the right side view, you can see, and you know, possibly you can imagine that the curvature of the cylinder is going to make this point on this rectangular bar lower than the actual top of the cylinder. But we don't have to draw it that way. Okay, so we can draw it straight across. All right, same thing over here. Now this is maybe a better representation. I want you to look at the left side cylinder. So this is a true representation. So when we have a cylinder intersecting a cylinder, we're going to have this curvature where the cylinder blends into or intersects with the other cylinder. All right, we can draw that, but we don't have to. And in fact, we can just draw it as a straight line across. Okay, these are other examples for cylinders intersecting holes. This is the true projection, right? And this is the preferred projection over here. And I think you'll see in all these cases, this is basically a time-saving method for the drafter, a shortcut, something to make it, easier to draw, really. But also it can be easier to understand because this is kind of difficult to get your head around sometimes what this in fact means. And this is a more straightforward. Okay. Now, this is important. We will have objects that we're going to be drawing in class like this, especially when we get to the section view chapter. When we have cases where we have features that are not aligned with the projection plane, okay? So in this, let's look at the feature with the 3 arms over here. So the projection plane between the top view and the front view is going to be a horizontal plane tracing out right where my arrow goes. Okay, so there's the projection plane. This feature right here, this arm, is not oriented parallel to the plane of projection. So if we drew it down here in its true projection, it would be kind of weird. It would be kind of foreshortened and off-center, and it just would not be clear. So we are allowed to draw this view as if this object is rotated up to the top and projected straight down. Okay. Now, clearly, this is not the true projection of this object, but this is how we, in fact, would draw it. Same thing over here. We have another feature here. This feature with the hole and the boss, the square boss, is not in alignment here, but we're allowed to draw this like this as if it was in alignment. Same thing with these ribs. Now, this is done a lot, and you'll do it in class in some of the drawings. This rib is rotated parallel to the plane of projection, which in this case is vertical, and then drawn here. This hole is rotated through here and then drawn like this. Okay. Now, this can be a little bit confusing. Here's another way to look at it, exactly what's happening. Now, these lines, these arcs, and these projectors through here, we don't actually leave these on the drawing. These are just for construction purposes, but you can see what happens. And you can also compare, this is the true projection, and look at how confusing this is, how messy this is, and how difficult this would be to draw. This is the conventional method for this, okay? Here's another example with the ribs. Same kind of feature. So in the middle drawing right here is the true projection. And you can see what a mess this is. Look at this rib over here because we're drawing it projected from here. It's foreshortened and it's at an angle. And then we have this keyway over here that's projected through, and it makes all these hidden lines. And that's just messy. That's just yucky. This is how we would actually draw it. Okay. So the rib is drawn as if it's over in this position. The hole is drawn as if it's over here, and everything is balanced and symmetrical. The last example over here is with a lot of holes. Now, true projection, we show hidden lines for all the holes, but look at this mess. You can't tell which hole is which, right? So the conventional standard practice is we just ignore all these holes right here, and we only draw the hole at the 12 o'clock position, at the 6 o'clock position, and the main center hole. All right. So you should be happy about that because that's going to save you some time. All right. Moving on to runouts. I think there are some drawings where we actually have runouts that we need to confront. A runout basically is when you have a object with curved edges, with curved surfaces that are blending or intersecting with other curved surfaces or cylindrical surfaces. Okay. So there's a way to represent that, and I would, it's kind of difficult to see in this view. So I would definitely direct you when you have drawings like that to figure out how to draw. I would definitely direct you to the figure in the book in chapter 6 that shows this so that you can really study it and understand it. Here's a kind of a magnified representation of what the runouts look like when you draw them. And you can see what we're talking about is that little upturn right there, that little tick up is generated from this surface right here blending into the cylinder. All right. So that's a little uptick right there. Here we see it again. This is just the point of tangency is a little bit back from the center. Here, the point of tangency is at the center. All right. But it's identical. The little upturn turn, the run out looks identical. How do we construct that run out? Well, we construct it like this. We draw a quarter circle here, and then we trim it off so that it's basically 1/8 of a circle. We trim it off at 45 degrees. When we are doing this in AutoCAD, I will show you how to do this construction. Okay, so don't worry. I'll show you. There's some tricks that I want to show you. So I'll be able to show you when and if we're doing drawings with this. I think there are some, but don't hold me to that. All right. And so that concludes the our quick trip through chapter 6. While you're doing these drawings, please pay attention to the CAD standards that I have published on the Canvas website. They're going to greatly help kind of answer some of your questions about how centerline should look, how this view should look. All those things that run through your head. I would also strongly encourage you to keep your book open with you while you're doing the drawings. When I was doing these drawings, and actually when I was going through school, I used the exact same book. I used the exact same book. It was an earlier edition, but I still have it. And these are all the same drawings that I actually did, most of them at least. But what I always did when I had questions about how something should look, I always looked through the book to find a figure that would either show me that I was right or show me that I was wrong. So, you don't have to read everything in the book. The book does a great job of showing you figures and diagrams to help you understand graphically what you're supposed to do or what needs to be done. So I would say, to look, if you have questions about a feature that you're trying to draw or drawing, find an example in the book. Find an example that either supports your idea or that negates your idea. And then that's the way to go, because the figures in the book are correct. They're to standard, and they're according to the rules and guidelines that we're going to be using in class. Okay. So, I will be publishing another video shortly that's going to run through the CAD assignments, that you're going to be doing for the class. So I'm not going to talk about any of that right now. That will be discussed in the next video. All right. I'll see you then.